Hey everyone, what's up? Mrs. Crowley here. Alright, so I may not be in the classroom right now, but I'm going to do the best that I can to assist you in learning some of the content here on electron configurations. Alright, so you're going to need to have a copy of your notes that you took last class. I'd like you to also have a periodic table in front of you and the homework that you had from last class, and of course something to write with, okay? Alright, so I know that this material is very confusing when you first learn it, but electron configurations is actually pretty easy once you get the hang of it. I just need you guys to get the hang of it. Alright, so let's check this out. First of all, electrons don't necessarily travel in these perfect little circles, okay? They don't travel in perfect orbits, kind of like, you know, the Earth rotates around the sun and those perfect circular paths. They actually travel in these really peculiar shaped orbitals. All right, orbitals are the places where the electrons like to hover around and hang out inside of. So they have some pretty strange shapes. And then I went through and I taught you about each of the shapes. So the s orbital kind of looks like a sphere. And I want you to imagine taking a sphere and rotating it around in space. No matter how you rotate a sphere around in space, it's always going to look the same from every angle, right? Well, I hope you wrote this down in your notes. There is only one type of s orbital. So an orbital, by the way, is a place where you like to have the electrons hang out. But here's the thing about electrons, and I think this may have been a little bit confusing in the last note series that I did. Orbitals only like to have 2 electrons in them at any given time. 2 electrons max. So an s orbital only has one shape, one orientation in space. There's only one way that we can put the electrons in. We can only put 2 electrons max in there. Now when we fill an orbital with electrons, the thing that you have to remember is that electrons hate one another. Electrons have a negative charge. So if 2 negative charges get close to one another, what are they going to do? They're going to repel. So if we have 2 electrons that occupy this spherical shape, they're going to want to be on opposite sides at all times. And so in chemistry, we use these things called vectors. Vectors are arrows that show magnitude and direction. We're going to use a vector to kind of represent the spin or the way that the electrons are sitting inside of the orbital. So if we have to have 2 electrons occupying the same orbital, we have to make sure that the electrons are in opposite spin. So you may have seen that we'll put the first electron into an orbital in a spin up direction, but if we have to put a second electron in there, it has to be in a spin down direction. Now a p orbital kind of looks like a dumbbell, like 2 little eggs or something sitting right next to each other. All right, and they're not touching in the very, very center. So it's kind of like if you took 2 eggs or maybe 2 marbles and then you rolled them together and you made them touch. That's what a p orbital would look like. So as you can see from the picture here, I want you to look very closely. There are 3 different types of p orbitals. Now some of you guys are familiar with, like, if we draw an XY, you know, Y is going up and down and X is going across side to side. But did you know that there's also a Z axis? Z axis gives you the 3D perception. Z axis goes out away from you and back towards behind you, behind your back. So it gives us that 3rd dimension. Now, because there are 3 different types of p orbitals, there's one sitting on the x, there's one sitting on the y, and there's one sitting on the z. So if we ever have a p orbital, we would actually draw 3 different places or orbitals for the electrons to sit in. So a p orbital has 3 different ways, 3 different shapes that we can make those electrons fill into. Now, when we put electrons into a p orbital, there is a special rule that we have to abide by. You may have seen these rules in your notes from last class. All right, There's only 2 electrons max per orbital, we got that. And if they do occupy the same orbital, they have to be in opposite spin. That's the Pauli exclusion principle. But what I'm about to teach you is a very difficult rule. It's called the Hund's rule. Hund's rule says that when we fill an orbital that has like different types of energy levels, like the P can sit on the X, it can sit on the Y, and it can sit on the Z, so it has 3 different shapes. When we fill that orbital, we have to put 1 electron into each orbital, each different type, the X, the Y, and the Z, before you pair it up. So what does that look like? If we're going to put 1 electron into a p orbital, that's easy enough. We just take one of these electrons and we put it spin up. If we need 2 electrons, though, in a p orbital, you are going to go to the second orbital that there is, the second one, and you're going to put an electron there. Just because you can fit 2 electrons into a box doesn't mean that you're going to put them in the same box. You're going to put 1 electron into each orbital, just like this. Right? You see 1 electron in each orbital before you go back and you pair them up, spin down. So you see how I have 3 electrons in a p orbital, but what I did is I put 1 electron into each box first. Then, if you need a 4th electron, you're going to go back and start giving those electrons pairs. So the p orbital that you see I have drawn here has 4 electrons. This right here is the Hund's rule. 1 electron into each box before you pair them up. So an s orbital has 1 box. A p orbital has 3 boxes because in s there's only 1 type, a p there's 3 types. But as you can see here, the d orbital has 5 types, 5 different shapes, if you will. So if we needed to draw a d orbital, we would have to draw 5 boxes. And then if we have to draw an f orbital, good golly, we would have to draw 7 boxes. What do all of these boxes mean to us? Well, they actually do mean something pretty important. You see, the periodic table's shape is not random. It actually means something very important. The periodic table is broken down into boxes or blocks. All right, the first 2 groups on the periodic table, these 2 guys, these are called the S block. The big group over on the right side of the periodic table, excluding helium, we don't count helium, this is called the P block. The middle section where the transition metals are, this area is called the D block. And then this weird area down here where we have the lanthanide and actinide series, this is called your F block. Now, let's see if you remember something that you learned. An s orbital only has 1 shape, and an s orbital can hold 2 electrons max. Here's something that I hope you see. In the S block, you have 2 elements side by side. That corresponds with the 2 electrons max. Let's go over to the p orbital. Now the p orbital has 3 shapes, sitting on the X, the Y, and the Z. Each shape can hold 2 electrons. That would mean that we would have a total of 6 electrons max. Come look at the periodic table. Let's count across the P block. 1, 2, 3, 4, 5, 6. Let's go to the D block. Now a D orbital has 5 different types of shapes. 2 electrons into each one of those would mean 10 electrons max. Correct? Count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then finally, I think you understand the F has 7 different shapes and 14 electrons max. If you count across the F block, sure enough, you'll have 14 elements. All right, in some of your previous lectures that I have sent to you, you learned a little something about the history of the atom. And when we were learning about the history of the atom, we came across Bohr. Now, Bohr took electrons and put them in very orderly paths around the nucleus. All right, and the nucleus here in the middle has some protons and neutrons that I drew in. But I don't know if any of you guys have ever been taught this before, maybe like in elementary school or something like that. But there's a certain amount of electrons that can go onto each ring, like max. And then once you reach that max, then you have to pump out into another ring. I don't know if you guys knew this, but the first ring is only allowed to have 2 electrons max. So 1, 2. And then after you have those first 2 electrons into the first ring, if you wanted to add more electrons, you would have to go to like the second ring. And in the second ring, you can have 8 electrons max. Now, I don't know if any of you guys actually knew this from like some of your previous history, but here's the basic idea. In the first ring, again, repeating, there are 2 electrons max. And in the second ring, you can have 8 electrons max. All right, in the third ring, you can actually have 18 electrons max. And then finally, if you hit the fourth ring, that's getting pretty big, but if you do hit the fourth ring, you can have, let's see, what is it? I think it's 36 electrons max. Pretty sure that's right. Anyway, let me show you something interesting about the periodic table. You see, the periodic table is broken down into families and periods. Families run down. So like, for example, the last family on the periodic table, this backside over here, where we've got helium, neon, argon, krypton, xenon, radon, these are known as the noble gases. This is the noble gas family. All right, but periods run from side to side. So families run up and down. Sometimes families are sometimes called also groups, okay? But periods run from side to side. Now, in the first period of the periodic table, you're going to hit hydrogen, and then you're also going to hit helium. Now, helium and hydrogen both are kind of unique little weird kind of step cousins, if you will, of the periodic table. Helium, a noble gas, is located on the far right-hand side of the periodic table because he is non-reactive, just like all the other noble gases. So we like to kind of group up elements that are, similar to one another. And helium is similar to all the other noble gases because helium is non-reactive. All right, that's why helium is placed on the far right-hand side of the periodic table. But if we were going off of the shape of the periodic table as the primary indication of how we should be grouping elements, helium technically belongs part of the S block, because helium has electrons in the s orbital. But someone decided to move helium way over to the noble gases because he reacts, or rather doesn't react, just like all the other noble gases. And so that's why helium is pulled off to the side. But here's what's interesting about the shape of the periodic table. Here we go again. So did you realize that in the first period of the periodic table, you are only going to hit hydrogen and helium? That corresponds to the fact that the first ring of electrons around an atom can hold 2 electrons max. In the second ring, check this out. Look at the second period. In the second ring, we can have a maximum of 8 electrons, right? Well, look at the second period of the periodic table. 1, 2, 3, 4, 5, 6, 7, 8. Sure enough. But things get a little strange right around the third ring. On the third ring, you're going to have, as you can see, only 8. But I thought the third ring, like I showed you before, doesn't the third ring actually hold 18? Here's something bizarre that happens, and it involves the first rule of electron configurations. You see, atoms are kind of lazy. The first rule of electron configurations is that electrons have to occupy the lowest energy level first. So, here is an interesting diagram to show you all of the different energy levels for every single orbital. So, these are all the different types of orbitals that you have that the electrons can fill into. Notice on the left side, it's increasing in energy going upwards, in an upwards direction. So, the very first orbital that electrons can pump into would be the 1s orbital. Now I notice that it's missing from this little diagram, so let's just pretend that down here we have the 1s. And 2 electrons can fit into that s orbital. So if we need more electrons, the next orbital up is going to be the 2s. All right, and then after that orbital is all full, by the way, that'll be 4 electrons, we would actually jump now into something called the 2p orbital. And then after that, the 3p. And then after that, then the 3s, and then the 3p. Now here's where things get a little jumbled, and I want you to take special note of everything above that squiggly line. Do you notice, I don't know if you can tell, but I can tell, the energy levels start getting really close together. Do you notice that? Maybe this picture will help. You see, here's what is going on. You are going to put 2 electrons into the 1s, 2 electrons in the 2s, 6 electrons here, 2 electrons there, 6 electrons there, and then, do you see how the 4th energy level creeps in? You see, the 4s is lower in energy than the 3d. And the periodic table reflects that weird, awkward energy level change. Check it out. You see, electron configurations correspond to the energy levels that you're about to see being revealed here in my example. We always start our electron configurations with a large number in the front, and we will always start that with a number 1, because we always start putting electrons into the first ring. You see, the number in the front represents not just the ring number, but also the period number. And we start putting electrons into the s orbital, which of course corresponds with the first 2 elements on the periodic table being in the s block. Now I understand helium's over here, right? But I think I explained that pretty good, that helium is technically a member of the s block over here. Okay? And we can only have 2 electrons max in the s orbital, right? So that corresponds with the first 2 elements on the periodic table, hydrogen and helium. So when you place this number up high, the number up high represents the total number of electrons that are being pumped into that particular orbital. So the number in the front represents the ring number or the period number, the letter represents the orbital, and the number up high or the superscript represents how many electrons are in that orbital, and as you can see, that represents the element. If I were to stop right here at the electron configuration of 1s squared, that right there is the electron configuration of helium. But what if I want to keep going? Well, I don't know if you guys remember the Bohr model example that I was trying to explain, but the Bohr model can only have a maximum of 2 electrons in the first ring. And after you get those first 2 electrons in the first ring, if you need more electrons, you're going to have to add a second ring. And the periodic table kind of does that. You see, after we go through the first period of the periodic table, we're going to hit the second period of the periodic table. The number in the front of your electron configuration will switch to a number 2. We are going to pretend like we're looking at lithium and beryllium, okay? So notice you're in the s block. The orbital is an s. Let's do lithium and beryllium, both of them. So the number up high is going to be a 2. I want you to notice that the numbers up high represent the atomic number. What is 2 plus 2? That's 4, right? The atomic number for beryllium is 4. If we stopped our electron configuration right here, this would be the electron configuration of beryllium, element number 4. And if you're paying attention to your Bohr model, we would actually be sticking 2 electrons into that second ring so far, just like that. But what if we want to keep going? After beryllium, you're going to hit boron, element number 5. You are still technically in the second period of the periodic table, so the number in the front is still a 2. But you've hit the P block, so I'm going to put a P. What if we want to go all the way to the end and hit neon? Well, let's count. 1, 2, 3, 4, 5, 6. So the number up high would be a 6. 6 plus 2 plus 2 is 10, and that is the atomic number of neon. But what if I didn't want to go all the way to neon? What if I actually just wanted to stop, say, I don't know, let's stop at nitrogen. Let's stop there. So if I wanted to stop at nitrogen, stop right here, I would be 3 elements in, right? You see how the number up high on the last part of the electron configuration is a 6? Well, if I stop at 2p3, that right there would be the third element in on the 3p, on the 2p block. Stop right there. That is nitrogen. What is 3 plus 2 plus 2? That's right, it's 7. That's element 7. All right. Well, let's pretend like we did go all the way to neon. I'm going to switch that number back to a 6. Okay. Now, what if we want to keep going? Well, if you look at the Bohr model down here, I would have to add 6 more electrons to that second ring, right? And at this point, the second ring has 8 electrons. Second ring can only have a maximum of 8 electrons, right? So what do? Add a third ring. Now we're on ring number 3, aren't we? And the periodic table is moving to the third period. So let's pretend like we're looking at sodium and magnesium now. We would have to switch on our electron configuration to a large number 3 in the front. We're in the S block, so I'm going to draw an S. Let's do sodium and magnesium, so I'm going to put a 2. This right here, if I stopped right here, this would be the electron configuration of magnesium. Let's keep going all the way across. You're still in the third period of the periodic table, so it's still a large 3, but now you've hit the P block. Let's go all the way to argon. That would be a 6. What is 6 plus 2 plus 6 plus 2 plus 2? It's 18, and that corresponds to element 18, argon. Now I want you to pay attention to your Bohr model over here. We're on the third ring, right? You're going to have first 2 electrons here. That corresponds with your 3s. Now let me show you the 3p. 2, 3, 4, 5, 6. If you notice, your third ring right now has 8 electrons. And if you remember from a previous, from just before, I told you that the third ring can actually hold 18 electrons. So what gives? What's going on here? Why are we moving down after argon? Why do we go to the 4th period on the periodic table? That comes back to the darn Aufbau principle. This is weird. You see, after we get to the 3p orbital, the next orbital with the lowest energy level is actually the 4s. You see, it's not as clean and precise and perfect as you thought. So here's the general rule of thumb. After you hit 4s, okay, so think about that. You're on the 4th period. 4s is right here and right here. After you hit the 4s, you're going to be hitting the D block, right? Here's the rule. When you hit the D block, the number in the front, even though we're in the 4th row of the periodic table, the number in front will drop by 1. So element SC, element number 21, is actually the very start of what we like to call the 3D orbital. But that's not the only weird part. It gets even weirder when you hit the F block. So it's kind of hard to see on the periodic table in my classroom, so I do want to bring this up. You're going to hit the F block right at the 6th row of the periodic table. You see, the periodic table in my classroom has these two elements. Those are called lanthanide and actinide. They have those two elements sitting right here, which is technically in the D block. But you should realize that element 57 and 89 are the very beginning of the lanthanide and actinide series, which are your F block elements. So here's the rule. When you hit, after you hit 6s squared, which is right here at barium, after barium, you're going to want to go to the lanthanide. Lanthanide is technically the beginning of the F block. And here's the rule. When you hit the D block, you go down by 1. But when you hit the F block, you go down by 2. Lanthanide is technically the very beginning of 4F. Do you see how the number dropped by 2? And actinide right here, you see how you'll hit that in the 7th row? That is technically the very beginning of the 5F orbital. Now this picture periodic table, the periodic table I'm looking at right here, you'll see Lu and Lr, these two elements, are attached to the F block. But they're not technically members of the F block. These two elements are actually members of the D block. They belong right here. Crazy, crazy. And you're probably thinking to yourself, how the heck am I ever going to remember all of this? That's where this lovely little diagram comes into play. You see, this diagram is going to help you keep your electron configurations in perfect order every time. You just need to make sure that you're looking at this every once in a while to make sure you don't mess up. So it's pretty easy. You'll notice that all of your S's are going straight down. See that? Okay. And then all of your P's start in the 2nd period, those go straight down. See that? And then your D's start in the 3rd period, and they go all the way down. And then you only have 2 F's, and those go in the 4th and the 5th. Now, you have to go through the electron configuration in order, starting with the 1s. So it goes like this, 1s squared, then 2s squared, in diagonals, 2p6, 3s squared, 3p6, 4s squared, 3d10, 4p6, 5s squared. And you're thinking, there's no way I'm ever going to remember just by looking at the periodic table. But if I can do it, so can you. Let me show you how it works. 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared. Remember when you hit the D block? 3d10. Then it goes back. 4p6. 5s squared. Remember how you have to go down? 4d10. 5p6. 6s squared. Coming down to lanthanide. Remember you have to go down by 2. So this will be 4f14. Then where do I go? Do you remember? You're in the D block, technically in the 6th row. So this will be the very start of 5d10. Then it jumps back to 6p6. 7s squared. Coming down here. Go down by 2. 5f14. And remember here, this will technically be, see how you're in the 7th row, this will be 6d10 and then 7p6. Here's something you should also note. So far, we have not discovered any elements that have more than 7 rings of electrons. Remember, the Bohr model corresponds with the electrons that you see in order of their electron configurations that you see right here on the periodic table. Alright, you guys, grab your homework. I think you'll have a better understanding of it now. Let's give it a go. Number 1 has you guys doing magnesium. Now, magnesium has an electron configuration of 12. Alright, find it on the periodic table with me, okay? Alright, that means since its atomic number is 12, it's going to have 12 electrons. Let's see if we can find it on the periodic table and correctly identify its electron configuration. Okay, here we go. Start with hydrogen. You have to start at the very beginning. So this will be a large number 1. Remember, helium is actually kind of like it's over here. This is the S block, right? So this will be an S, and we have 2 elements going across, so that'll be a 2 up high squared. After that, we're going to hit the second period of the periodic table, so this will be a large number 2. Large number 2. Okay. We're looking at lithium and beryllium. We're in the S block, and there's 2 elements, so I'm going to put a 2. After that, we're going to hit boron. We're still in the second period of the periodic table, so it's still a 2, but now it's a P. Let's go all the way across. 1, 2, 3, 4, 5, 6, so that'll be a 6 up high. And then finally, we're going to drop down here to the third period of the periodic table, so a large number 3. You're in the S block, and let's hit magnesium by putting a 2. There you go. That's its electron configuration. But how does that look when we do the orbital notation, the thing with the arrows? Okay, do you remember that an s orbital has only one shape? That corresponds with one box, if you will. All s orbitals only have one box. So we'll pretend that this is like a 1s. Okay, this box right here is 1s. You'll notice that we also have another s on the 2s. So I'm going to draw another just one box, and that'll be our 2s. What do we do for a 2p? Do you remember how there's 3 different types of p's? We are going to draw like 3 orbitals, 3 different orbitals for the 2p. All right, the 3s would correspond with just one box. Now sometimes orbital notation is done in boxes, and other times they're done on lines like what you see up here. You'll notice that the 1s only has one line, the 2s only has one line, the 2p has 3, and the 3s only has one line. You see that? So it kind of did most of the work for you. So how do you get 2 electrons into the 1s squared? Well, we always put the first electron spin up, arrow up, and the second electron spin down. We're set. 1s squared, done. Let's do the 2s squared. First electron spin up, second electron spin down. 2s is done. Now let's do the 2p. Now the 2p is completely full. It's got 6 electrons. So this will be pretty easy. Spin up, spin down, spin up, spin down, spin up, spin down, and the 2p is done. Let's do that last one, the 3s. Spin up, spin down, and you see how it's got 2? Done. Well, guys, that's all I've got for today. I really hope this helped. I think you have plenty of information to get started now. And good luck, and I hope to be back very soon. I miss you guys. Take care.